For half an hour, we'll talk about cones. And there's plenty of cones. They are very nice objects. They're very, very, very useful. We'll start with constants you probably know very well already. If you have k vectors in Rn, you take their combination with weights that we call lambda from 1 to k as well. This weighted sum, if you only impose a constraint that lambda is non-negative and no other constraint, what it gives you is a conic combination. This is obviously a difference from convex combination where you also require the lambdas to sum up to 1, not only be non-negative. The conic hull of a set of points, or the conic hull of a set, is the set of all conic combinations of any 2 points in the set S. So again, you can translate it from the idea of convex hull, but this time you create all possible conic combinations instead of convex combinations. So again, you only require the lambda, the multipliers, to be non-negative and not sum up to 1 necessarily. So if you had a set like this, the convex hull would be something very smooth and very nice like that. But the conic hull instead, it will be something, we'll see in a bit why that's the case. It's going to be such that for any 2 points, you not only take all the convex combinations, but actually all the conic combinations. So you can actually scale them down or scale them up in such a way that they are on this same half line, but anywhere on this half line. So the conic hull is basically taken as, let's see if I do straight enough lines. It's going to be this object and everything in between. So this is a conic hull of any set S. A cone is a set that has a very specific feature, which is for every x, for every point in that set, any scale up or scale down of the same point for alpha greater or equal than 0 is also in the cone. That is obviously a cone precisely for this reason. Any point you have belongs not only to the set, but to the whole half line starting from the origin and going through the same point. All such sets are called cones, and not all of them are convex. So you can easily have another object like this, well, an additional object, which you take the union with this other object. These two in union form a cone, but it's not obviously a convex cone. Am I making sense so far? First exercise I have for you is the following. Is the conic hull of set S the same as the convex hull of the conic hull of set S? Intuitively, that seems reasonable, right? I mean, we take conic combinations or convex combinations here and there. We always end up with a set that is regular enough. It doesn't have holes and doesn't have space between, etc. But can you prove it rigorously? And second question, is the conic hull of S equal to the conic hull of the convex hull of S? That's a slightly different question. Does anyone have a short proof? So do you have an answer? We went a bit fast, so let me write stuff here so that we know what we are talking about. What is then the convex hull of any set? So the convex hull of any set S is equal to, let's write it here, the set of all points written as lambda prime x prime plus lambda double prime x double prime, such that x prime and x double prime are both in S, and lambda prime, lambda double prime are both non-negative, and in addition, lambda prime plus lambda double prime is equal to 1. Do we agree on this? The conic hull, we just saw it, so let me write it out explicitly as well, is simply another set that is similarly described. The only thing that's missing, we can just copy-paste this if we had copy-paste on blackboards without this last bit. So is the set lambda prime x prime plus lambda double prime x double prime such that x prime x double prime in S, lambda prime lambda double prime greater or equal than 0, and that's it. So because lambda prime plus, because lambda prime and lambda double prime have an extra constraint for the convex hull, what can we conclude? For any set, the convex hull of S is what with respect to the conic hull of S? Not necessarily a proper subset. So that's one thing we could conclude already. So if any set, let's pretend these are just any two sets. If the first set is a subset, non-proper, of another set. So if I have two sets A subset equal B, can I say that the conic hull of A is a subset of the conic hull of B? That's easy to prove, right? So that means that the conic hull of the convex hull of S is going to be a subset of the conic hull of the conic hull of the same set S. Right? And now what happens is that the conic hull of a conic hull of a set is simply just the conic hull. So at least we have one side of the equation, which is the conic hull of the convex hull of S is definitely a subset, possibly equal to the conic hull of S. Now we have to prove the opposite, right? How do we do this? Yeah, now we need to prove, we only prove this side, we need to prove this side. It should be easy, right? What can we say about the convex hull of S and S itself? As a superset. So we have two sets, one on this side, one on the other side. We take the conic hull of both, and we get the con of the convex hull of S is a superset of the cone of S. Both superset equal and the subset equal. The proof is done. Does it look all right? Does it make sense to everyone? What about the, yeah, I know. What about the second question? No, sorry, you have a question about this? We prove the, yes, okay. Yeah, we prove the second now, wait a second. Yeah, that's, no, yeah, sorry, no, that was this was, I just flipped them in LaTeX a while ago because actually the first one is easier. How do you prove the first one? Yeah, sorry, so you were looking at for my fault, you were looking at the wrong one. We proved the second. Prove the second hypothesis. How do you prove the first hypothesis? That's even easier. I mean, that's easier.
Conic hull of S would always be a convex core because we are taking all convex conventions.
Right.
And then the convex hull of a convex set
is the same set, exactly. Okay, so examples of cones, they might be all redundant to you, but we need to warm up just for the next part regarding cones. So Rn is a cone, so the whole n-dimensional space is a cone. The first orthant of any n-dimensional space is a cone with a vertex in the origin. The set defined by the origin is a cone because it satisfies condition we said about the cones. The fourth set is not a cone because it's easy to see that if this is the set, this is x2 and this is x1. Clearly, this point belongs to the set, but not the whole half line belongs to the set. So clearly, this is not a cone. The set, the second last and the last set are also cones. The first one can be easily described like this. One is the union between this line through the origin and another line through the origin. These are cones. They're not convex cones, but they are cones. The last set is just a half line, because I'm imposing every coordinate is not negative. Okay? Let's do this quickly. Which ones here are non-convex sets? So they are sets. Some of them are cones, some of them are not. Which of these sets are non-convex? Basically just the second last, right? The second last, yes. And what is their convex hull? Remind you, it was this guy over here. What is a convex hull of this set? It's a whole R2, right? Take combinations of this sort, we get the whole R2. You still here? Everything good? Okay. So this set that was not a cone, that set is in fact convex, although it's not a cone. What is the conic hull of this cone? And what is the convex hull? Oh, sorry, what is the conic hull of this set and what is the convex hull of this set? The convex hull is easy, it's just the set itself because the set itself is convex. The conic hull is what? So the conic hull of only that, this is tricky. X in R2 such that x1 greater or equal than 2. So one hypothesis is that it's equal to R plus Cartesian R. Is that what you said? So, oh, sorry. Let me write it explicitly. So x in R squared such that x1 greater or equal than 0. Do you agree? Does that mean that the point 0, 1 belongs to this? This 0, 1 belongs to this set, right? Does it belong to the conic hull? You can't find this point as a conic combination of any points in here. So what is it going to be? Do we just take the strict inequality? What do you mean and? Very good. So it's a strange set. It's convex because it's a cone. It's convex because it's a convex cone. But the funny thing is that it's a set that's written like this with a strict inequality plus a single point. And this is a cone. Well, it's not a closed set. Okay, another example. Any set described by a single equation, p of x equal to 0, where p is a polynomial that is homogeneous, that is a polynomial where every term has the same degree, is a cone. Why is that the case? Because if I take any alpha x, so if x belongs to the set S, to the cone K, well, this is only true if p of x is equal to 0. But that means what? It means that p of alpha x, every term has the same degree, is going to be equal to alpha to the whatever. K, it was the degree of the polynomial, times p of x. equal to 0, so that point also belongs to the set. So that set is a cone. It's not a random reference because if you think about the discussions on perspective reformulation, this is roughly what happened. There was a non-homogeneous inequality, y greater or equal x squared, and then all of a sudden it became a homogeneous inequality. X squared less or equal than y times z. It's not a coincidence. So I hope all of this was, if not obvious, at least intuitive enough for all of you. Now, in nonlinear optimization and in mixed integer nonlinear optimization, one set that is very, very common is the second order cone. One type of cone that is very popular is the second order cone. It's defined by both of these two modalities. They're really equivalent. So it's defined by the set of n-dimensional points such that one of the dimensions, so xn is greater or equal to the norm of the vector composed by the remaining n-1 coordinates. And this suffices. And if you take, I think we saw this picture in this course before, and you must have seen it elsewhere too. If you take x1, x2, and n is equal to 3, so this is x3, this is simply going to be the set of points for which x3 is greater than or equal to a function that very much looks like this cone. I mean, if you draw it, I mean, if you visualize it, much prettier than this, but this is more or less what happens. So everything inside this cone satisfies that. Satisfies that inequalities. Be careful to one thing. You can also express the same condition by squaring both sides of the inequality. The only thing is that you must be careful that xn must be non-negative. The problem otherwise, and I think it was the subject of one of the exercises, this set without this condition would actually be non-convex because it would take the bottom cone as well. So if the solver, if Ample tells you this is a non-convex set, it might be because you forgot to impose that xn is non-negative. And this happened before. There is another type of second order cone. It's pretty much equivalent to this type of second order cone, and it's called rotated simply because it's actually rotated. So you take this cone here, and instead of making its axis equal to the x3 axis, you rotate it in such a way that its axis become the line that is the bisector of the x1, x2 Cartesian plane. So you just pull it down like this, 90 degrees. And in most solvers and in most modeling languages, what you need to do is either you write it in this form with this inequality. There's a peculiarity here that is the 2 multiplier here is necessary. So the inequality is basically the same sort of thing. The norm of the remaining n-2 variables is less than or equal to the square root of 2 times the product of the last 2 variables. Or equivalently, well, you just square again the two elements, but I think you need there xn minus 1 greater or equal than 0 and xn greater or equal than 0. So in other words, you're always only taking x1 and x2 in the first orthant. It doesn't matter what you take for the rest of the variables. So x1 through x minus 2 included don't need to be non-negative. The full cone is actually going to be, with those variables, unconstrained in sign. The reason why there's a 2 here is that it's only a standard, but it basically means that the cone you're going to get is actually a cone. It's a rotational cone, and it's really the rotated version of this cone here. If you didn't put a 2 there, you would get something squeezed on one axis. The way that most solvers use or take information on rotated second order cones is by reformulating it so there's a 2 there. So there's a lot more stuff happening in the solver that needs to have that form of, that sort of formulation. So on a practical side, the second order cone in a modeling language can be specified as is. if you go as far as doing these non-intuitive inequalities, the solvers will somewhat reformulate everything. So for instance, the second last inequality is a cone, but it's going to be reformulated in this form. So the solver will just create two new variables at y1 squared plus y2 squared, less or equal than 2 times x4 times y3. And the reason why y3 is introduced is not only because we need a 2 before this product, but also because solvers don't like cones where the variable in the last product term is one of the variables appearing in the left-hand side. So they basically say, no, let me put just the new variable there, and then I just say that the new variable is simply equal to the old variable. This is only done by solver to, first of all, simplify and not write extra lines of code when not necessary, and then just add linear constraints. An extra linear constraint is not really a big price to be paid. In the example you saw, some of you wrote on Tuesday last week, there was that sort of conic inequality that we needed to add. And there was a square root, and solvers already don't like square roots to begin with. They think it's just a nonlinear problem, they don't want it. But if they manage to catch a quadratic problem, then all sorts of stuff will happen, and they like it better. But also the problem there was that under the square root, there was a sum of two squares, and the squares were of differences of variables and not just single variables. Some solvers are not as smart as to understand that this needs to be reformulated. So in this case, it should be you who will reformulate this in this way. So this is a real second order cone, non-rotated. The rest is just linear constraints. And one last thing not to be forgotten, Dij was fine there without a sign constraint, but it needs to be added here. Otherwise, again, you get a non-convex constraint. So second order cones can sometimes be used to express the fact that a variable needs to be greater than or equal to the norm of a given vector. Because that is the norm, the L2 norm up there is simply exactly the square root of what we saw before. But there is one extra, there are several applications where instead of taking the L2 norm, sometimes you are interested in LP norm with P greater than 1. In that case, you still have a norm that is a relatively well-behaved norm, and you can still have conic constraints that do the exact same thing. You just need to formulate them this way. You have to be careful that there's an absolute value sign here because P might be just fractional and stuff like that. But that's also sort of, that is also something that can be done for applications. And xn here, again, needs to be declared non-negative in case you don't use the square root. I'll discuss another two types of cones. The power cone is described by that single inequality in three variables. It's a sort of generalization of the rotated cone where instead of having on one side, you don't have a product between x1 and x2, but x1 to the alpha times x1 to the x2 times to the power of 1 minus alpha. And this is a generalization because in the case of second order cone, you have alpha equals 1/2. And so x1 to the 1/2 times x2 times 1 minus 1/2 is still x2 to the 1/2, which means this is the square root of x1 times x2. So for alpha equal to 1/2, you get back the rotated second order cone. In general, you can have as many terms in the product as you want. You can still have an inequality describing a cone, so it will be homogeneous again, which means that the sum over all the alpha j is equal to 1. So that on this side you have a term of power 1. On this side you also have a product with a monomial with degree equal to 1. This is a rather esoteric form of cone, but it's useful because you can model a lot of constraints that happen in practice using precisely this. So the constraint of absolute value of p less or equal than t with p greater than 1 is a convex constraint, and you can reformulate it as a conic constraint by just saying that t1x are a triplet that simply belong to the power cone with parameter alpha equal to 1 over p. And the same holds for other cones. So for other constraints, sorry. So t greater or equal x to the 1.5 is another convex constraint that can be formulated as a cone. For now, I think we are looking at cones where only two variables are involved, and the second term here and the second term here are simply equal to 1. But in principle, all of this stuff can be used in such a way that instead of that 1, if you have, for example, binary variables, you can generate a form of perspective inequality simply plugging in your binary variable, and that's going to make your constraint a lot tighter. The p-norm cone can be reformulated as a power cone by adding new variables Ri and a new constraint that says the sum over I of Ri equal to t. Another nice type of cone with the same opportunities as all the other cones is called exponential, and this time it's not it doesn't entail polynomial or quadratic inequalities. It needs to use the exponential function. So the definition is actually a union of two sets, but the most important part is clearly this inequality, x1 greater or equal than x2 times e to the power of x3 divided by x2, which, think about it, is the perspective function of e to the x. Again, this is not a coincidence. You can express convex constraints like this as cones. An interesting function that's used in applications is the entropy function minus x log x, which if you have a constraint of the form x less or equal minus x log x, then you can reformulate it, you can massage it a little bit, and it becomes a function, a constraint that can be formulated as a cone. And for those of you interested in seeing what it looks like this. I mean, it's a bit boring. Everything looks like a cone, but again, there are very nice properties that have to do precisely with the fact that these objects are cones. So if you wanted to take a completely different point of view, you could argue that many convex optimization problems can be simply formulated as problems with a linear objective function, and the constraint, the feasible set, is basically the intersection of two sets. The first set is described by an affine subspace, so a system of linear equations with 1, 0, or infinitely many solutions. The intersection of this affine subspace with a cone. The cone doesn't need to be a single exponential cone. It could be the Cartesian product of multiple cones. So you could have variables that are simply constrained to be non-negative. You could have another subvector of variables that need to obey a second order cone. This combination, this Cartesian product of cones, gives you a cone, which falls back into this sort of classification of convex optimization problems. So cones are important because you can easily solve optimization problems more efficiently if you use information regarding cones within the problem itself, or you can make it up with the problem. So I think one of the fundamental observations that need to be done here is the following. For any convex function g, and if g is a convex function, then this is an only one-way implication, as we saw in the tutorial on Saturday, then g of x less or equal than 0 is a convex constraint. If g of x less or equal than 0 is a convex constraint, so if g of x is a convex function, then this inequality, this linear inequality, is valid, and it's one of the so-called outer approximation cuts. And this thing should fall out of your ears because you've heard outer approximation a few times now. The exercise that we can leave it for the last part, I would like to do some visual experimentation with you. Take a very simple constraint, x squared less or equal than 1. X squared is a convex function, so x squared less or equal than 1 is a convex constraint. The outer approximation cut for this constraint at x star equal to 4, you just write it out, the g of x star and the gradient of g at x star, what you get is a very loose inequality. X less or equal than 17 over 8, which is more than 2. Right? It's trivial to see that x2 less or equal than 1 is obviously implies that x is less or equal than 1. So what happened here? Something very easy happened. So if this is x2 equals x1 square, or not really matter, this is the square function, and this is 1. Similar to the exercise we saw last time with quasi-convex functions in the tutorial, what is the feasible set for this constraint? What is the set of points satisfied by the constraint? If this is 1, then obviously this is 1 because this is a parabola. So the half line that begins at 1 and goes backward on the real line is the set of points satisfied by x squared less or equal than, actually no, because then you get this as well. So actually no, it's a segment. But this doesn't matter. Take x squared, x star equal to 4. You get a point here somewhere. You take the tangent to that curve at x star equal to 4, what do you get? Well, you get a tangent, obviously. The tangent looks like this. It's a linear function. The linear function with a constraint that linear function be lesser than or equal to 1 gives you all the points of that line, of this line, this tangent line, below this line. That gives you this constraint. So if this is 1, obviously my drawing skills are horrendous, and this is supposed to be for x star equal 4. This is 2.125. So it's obvious that if you take an x star far away from the boundary, you're going to get an outer approximation cut that is loose. So in general, if you take any convex set like this and your x star is somewhere here, the outer approximation cut is going to look like this. You wish it was tangent like this, but it's not. Almost all the time. There are cases in which it doesn't happen. So if instead of saying gx less or equal than 0 for g of x defined as x squared, if you did instead, let's take the square root of this, of x squared less or equal than square root of 0. What you would get is absolute value of x less or equal than 0. Come on. That should have been a 1, sorry. So g of x less or equal than 1, this is the square root of 1, this is 1. What would you get then? You would get a curve, a function g, square root of g of x, such that now the curve looks very straight. This is 1 and this is 1. Now take another approximation at x star equal to 4. What is it going to give you? A tangent curve that basically follows the straight line. And the tangent curve is just like this, so it will give you exactly the sort of outer approximation cut that is as tight as possible, regardless of how x star is far away from the boundary. So this is the case in which you actually get this sort of outer approximation cut. Do you agree? This was a trivial example, but we could make it much more complicated with this wall of formulas. If you take, we can actually generalize it to any quadratic constraint with some conditions. So let's take any quadratic constraint written like this. Suppose that there exists, that you can reformulate and rewrite this convex quadratic constraint, so Q is positive semi-definite. You can rewrite it in such a way that you no longer have the square terms separate from the linear term and separate from the constant term, but rather you get a form of, you rewrite this as x minus x bar transpose Q times x minus x bar. And you can do this if you know where this quadratic function has its minimum, and its minimum is going to be in x bar. And you can, in general, rewrite this paraboloid in a way that you know where the minimum sits, and you know that the constraint is going to be this new rewriting less or equal than alpha. We just rewrote the constraint. We didn't do anything to it. The problem is, the cooler thing is that if you take another approximation of the constraint written in this form, you're obviously going to get exactly the same other approximation you will get with the original constraint. So you can do the derivation yourself, but obviously this is going to be the case. So this form that you see at the bottom is obviously going to spell out the same quadratic and linear coefficients and the right-hand side as this for the original, the outer approximation cut on the original form of the quadratic constraint. So we didn't do anything here. We just wasted time trying to find x bar and alpha. Now, suppose since we already wasted the time, let's suppose that there exists actually x bar and alpha, which don't always exist necessarily. So if you continue doing this, you're going to get this form of the other approximation cut. So this is the other approximation cut, which you find by using x bar and alpha instead of the original coefficients. Now do the same trick we did there. You take the square root of both sides. Why can I do this? Well, because fortunately, this form of the quadratic constraint is such that since q is positive semi-definite, this term on the left is always non-negative. So you can always take the square root. Otherwise, we would be in trouble. But so let's take the square root of the left-hand side, and let's take the square root of alpha, which is the right-hand side. This is still a convex function. And if you derive the outer approximation cut for this constraint, what do you get? Well, we'll spare you the derivation. You end up with something like this. What is the difference you notice between this new outer approximation cut and the outer approximation cut you get from the reformulation, but without putting in the square root? And can you say that one is better than the other? So there are things that are in common and things that change, right? So the left-hand side is the same. Yeah, I want you to look at the green outer approximation cut and the blue outer approximation cut. What are the differences? The left-hand side is the same for both, right? If there is a difference in the left-hand side, it's a typo that I wrote. This part of the right-hand side is the same. It's in common with those two. The only difference is this long square root against that 1/2 times alpha plus 1/2 times that expression. Can we say that this is always better than that? And why? Alpha is a positive constant. What is I can hear that. Those two are common formulas. They are operations on two elements that give you something about those two elements. What is the first part? What is the green part up there? It's 1/2 times alpha plus 1/2 times something else. Isn't that the arithmetic mean of those two numbers? And this is the geometric mean, which is always less than or equal to the arithmetic mean, which means that this is always stronger than that. Okay, there's a couple of other nice things you can do with quadratic constraints, which again put us back into the fangs of cones. So this is a much more popular technique, which is actually commonly used in many optimization solvers that solve mixed integer quadratic optimization problems. So if you have a problem with both linear and quadratic and convex quadratic constraints, and you also have binary variables, so if you have a mixture of a discreteness and quadratic convex constraints, then this is a sort of technique that is very much used by a lot of the commercial and open source solvers. Take again a quadratic constraint, any quadratic constraint like this. Q is positive semi-definite, so this is a convex constraint. If Q has a lot of terms, so Q in general has n squared terms, where n is the dimension of the problem, number of variables. If Q is dense, And this doesn't happen very often in practice, but it does happen from time to time. What can you say about the other approximation cut? The other approximation cut will have coefficients for x, this is a variable x, with a lot of terms. So Q, if Q is dense, then Q times this guy over here is going to be dense as well. So we'll have about n, an order of n terms. The problem is, if you, many of these solvers do usually, if you add other approximation cuts this way, you're going to end up adding a lot of inequalities to the problem, to the linear relaxation of the problem, that contain a lot of terms. If your problem has 10,000 variables, then you're going to get a lot of cuts, each with 10,000 variables. That's a lot. Usually, solvers do not like, I mean, they handle constraints like this, but they don't like them. So there's all sorts of numerical problems. The efficiency is impacted precisely because they have to handle a lot more coefficients and stuff like that. But in principle, you could do the following. If Q is positive semi-definite, you could decompose it. You could do an LDL, a Cholesky decomposition, so you get Q as the product of two matrices, L and L transpose, where L is lower triangular. You have to be careful doing these things because there's all sorts of numerical problems hiding in there, but there are robust enough methods to do so. So in principle, now you can rewrite the quadratic term, the dense quadratic term, which has a lot of terms qij times xi times xj. And you can rewrite it by introducing new variables y, where y is simply equal to L transpose times x minus x bar. So if you take this quadratic form that we just introduced, then you could easily rewrite it like this. And now you have another quadratic constraint whose matrix is diagonal, because it's simply the inner product of two vectors y and y. So it's like having y transpose qy, where q is simply a diagonal matrix. This is not necessarily a much better behaved constraint, because you still have n instead of possibly n squared terms in there. But the other approximation cut, if you take the gradient again and everything, will have probably many terms again. A small digression, as I said before, x bar and alpha sometimes do not exist. And this happens where some conditions on the eigenvectors happen. And for instance, you can easily see that you will not be able to find an x bar and alpha from this inequality. This is because x3 is greater than or equal to a paraboloid function. So you won't be able to take the square root of this, because x3 could easily make the whole left-hand side negative. So just to warn you that this is not always possible. However, once you have a quadratic constraint rewritten like this with extra variables y, and the y's are simply subject to linear constraints that translate them back into x, what you can do is the second step. So after the diagonalization, what you can do is reduce this to a conic constraint instead. This is extremely easy. If you have a constraint y transpose y less or equal than alpha, you can easily translate it into a conic constraint by putting any variable you want here and simply fix the variable to 1. So you will get a conic constraint. Just to slow down a bit, I gave an example, but the inner product of y and y, so y transpose y less or equal than alpha, can be turned into a cone, and let me write it down explicitly. Sum of I from 1 to n of yi squared is less than or equal than alpha. This is what I just wrote. What I could do is introduce w and just rewrite this cone, just rewrite this constraint like this. All you need to do afterwards is simply say that w is, yes, it is a variable, it's part of the problem, but it's also constrained to be equal to square root of alpha. So nothing changed really, but you introduce the variable and you make this constraint look like a cone. It is a cone, and it can be used for other purposes. Now the complicated part comes. Once you have this cone, there's a very nice construction, and this all may look a bit exotic because we really changed a lot in the original quadratic constraint, but this works in practice. And what works is the following. You take this cone, and this cone has n terms on the left-hand side and 1 term on the right-hand side. So these, I mean, if you originally had a quadratic constraint with 1,000 terms, now you have a sum of 1,000 yi squared terms. This is fine for a continuous problem. Solvers usually handle these cones relatively well. With mixed integer second order cone problems, this doesn't happen very often, but you can decompose this cone by reformulating it this way. So you take that cone over there, just a copy on the blackboard, and you rewrite it introducing extra variables v. Now the cone is rewritten in a single linear constraint, the sum over 2 times the sum over vi variables less or equal than w. This is a linear constraint. And then you have as many small rotated second order cone for each of the n variables. And these new second order cones contain the new variable vi, but also the yi that was appearing in the original sum and the w that is appearing on the right-hand side. Do you believe that this is actually, so this constraint can actually be proven to be equivalent to the original one? What happens if you don't believe me? Take the sum of all this second class of constraints. What do you get? So if you take each of these n constraints and you sum them up, you get on one side the sum over the left-hand side, so the sum over I from 1 to n of yi squared, right? On the right-hand side, you get 2 times the sum over vi times w. But the first constraint, the linear constraint, says that this guy over here is less than or equal than w itself. So what you get back is precisely w squared. This is only part of the proof, obviously. So if you start from the 2 bottom constraints, you get to the first, but there's a way to prove the other direction as well. The important thing is extremely practical. So if I didn't try it on real software, I would think that this is all junk. But if you go from this quadratic constraint and you reformulate it this way, and you end up with a lot of extra linear constraints, and then another linear constraint, and then a lot of small rotated second order cones, what happens is that the solvers, who are very, very good at exploiting integrality of the problem, together with whatever constraint that comes in, linear constraint that comes in, is going to solve the problem in much less time. And this all because we turned a single quadratic constraint into a lot of small second order cones. These second order cones all have 3 variables, 1 square on the left-hand side, a product of 2 variables on the right-hand side.